So good evening, everyone. I'm Emilie. I'm a postdoctorate student, and today I'm going to present to you a part of my PhD results, which I defended a couple months ago, on the treatment of membrane concentrates using water oxidation. So the industrial development has led to an increase in the generation of wastewaters, and these wastewaters are difficult to characterize and to treat because they contain organic, inorganic, and refractory compounds. When they are not sufficiently treated, these wastewaters represent a danger for the environment and for the human health. And the regulation has become stricter over the last decade, so the industries have decided to implant concentration processes in order to generate large volumes of clean water. And these processes are mostly membrane processes. Our goal was to develop a flexible and global treatment path in order to treat the non-biodegradable compounds of industrial effluents, with a final objective to be able to discharge all the treated effluents to the environment, and we focused our work on 6 strategic industrial effluents. So the first step of the treatment path is the use of membrane processes. This part of the process will enable you to create a large volume of permeate with excellent quality. However, concentrates will be produced, and they are highly polluted. We propose to treat these concentrates with water oxidation in order to remove the organic fraction of the pollution. And when the conditions of concentration are between 10 and 100 grams of O2 per liter, this process can be with lower energy costs. So the global treatment path will allow you to remove the organic fraction of the membrane concentrates and reduce the energy cost of the water oxidation, since you have a membrane process before the water oxidation. And we wanted to study the performance on each industrial effluent that was previously concentrated by membranes. So we chose our effluents with great variability in order to study the robustness of the treatment path. And we chose to work on high produced flow rates at industrial scale, where the membrane processes are already implanted on the industries with different pollutions in order to have different types of organic pollutants. And so we decided to work on landfill leachates, pharmaceutical effluents, bilge wastewater, dairy wastewater, a complex industrial effluent, and a paper effluent. So water oxidation is an oxidation reaction that occurs in liquid phase, where the dissolved oxygen from air will degrade the organic fraction of pollution. The pressure of this process is between 2 and 30 megapascal, with temperatures between 150 and 300 degrees Celsius. It's suitable for concentrated effluents like membrane concentrates, with chemical oxygen demand between 10 and 100 grams of O2 per liter. So we first studied landfill leachates, and with the use of bibliography, we wanted to work on different temperatures and pressures. And we used a lab-scale reactor that is composed of a supervision screen for temperature, pressure, and stir speed. The reaction occurred in a reactor with a heating furnace, and we had 2 gas cylinders with or without oxygen. So each experiment was separated in 4 steps. We had a first step of heating. So here the duration will depend on the temperature. It's a duration between 40 and 90 minutes for temperatures between 200 and 300 degrees Celsius. This step occurs without oxygen and under a pressurized system with nitrogen. When the temperature is reached, we inject the oxygen. In our case, it was air. And then the oxidation starts. We performed an oxidation with a long duration during 6 hours, and we withdrew several samples each 90 minutes to characterize the organic fraction through total organic carbon, chemical oxygen demand, and fluorescence spectroscopy. At the end of the reaction, we cooled the reactor, and we did a total withdrawal of the reactor. So now I'm going to present to you the results, a part of the results with the effect of temperature, the comparative study of the effluents, a part on the fluorescence spectroscopy, and the mass balance of the treatment. So here we have the effect of the temperature on the on the 6 effluents that we treated. So we have here 4 effluents with a strong effect of temperature, which are the bilge wastewater, landfill leachates, the paper effluent, and the dairy effluent. And then we have effluents that have a lower effect of temperature, which is the case of the complex industrial effluent and the pharmaceutical sludge. Here we can see that there is no variation in the total COD removal at the end of the treatment as a function of temperature. Now, if we compare the performances for the different effluents at the time 0, which is the moment where we inject the oxygen, after 90 minutes, which is the shorter time that we have in our reactor, and after a long period of oxidation, we can categorize our effluents in 3. We have some effluents that have a weak effect of the heating period and a strong effect of the oxidation duration. It is the case of the paper effluent and the dairy wastewater. Then we have some effluents that have a strong effect of the heating period and of the oxidation. It's the case of the bilge wastewater and the landfill leachates. And then we have some effluents that have a very strong effect of the heating period and a weaker effect of the oxidation. And here it's the case of the complex industrial effluent and the pharmaceutical sludge. Here we can see that the water oxidation is not adapted for an industrial scale application because the heating of the effluent almost degrades the whole organic part of the effluent. And this is interesting because this effect is not always considered in literature. And we also have to study COD and TOC because we observed that we had different behaviors for both of these parameters. So now I'm going to show to you a part of the fluorescence spectroscopy results. So we based our study on the classical cartography from the literature that separates the organic fraction of the pollution depending on its complexity. We have here the humic substances, which are the largest organic compounds, and some of the small proteins at the bottom. So here we have the feed. So it's the dairy wastewater, and we can see that we have fulvic acid-like compounds, some small proteins here and here. When we treat this dairy wastewater at the lowest temperature, which is 200 degrees Celsius, we can see here that we have an increase of the fluorescence after the heating period and a modification of the repartition of the fluorescence. We also have a progressive disappearance of the soluble microbial byproducts over 180 minutes. And we have here, we can see that the fulvic acid-like compounds are not totally removed even after a long oxidation duration, even though there is a 70% decrease of the COD. Now, if we treat the same wastewaters at higher temperature, so 300 degrees Celsius, we can see that we still have this increase of fluorescence after the heating period, though it's lower than the one we had at 200 degrees Celsius. We still have the disappearance of the microbial byproduct-like compounds, though it's over a shorter amount of time. Here it's during 90 minutes. And we can see here that we have a very good removal of the fulvic acid-like compounds over a long oxidation duration that corresponds to a 93% decrease of the COD. So now if we want to know the mass balance of this global treatment path, we have here the effluents that are in order of CODs. We have here the concentration in TOC and COD for the water oxidation outlets, and then we have the quality of the global discharge, which is composed of the permeate and the outlet of the water oxidation. We can see that the paper effluent hasn't got the quality to be discharged to the environment. Now, if we consider the effect of the heating period we talked about earlier, there are 2 effluents which are not as interesting for an industrial application. It's the case of the pharmaceutical effluent and the complex effluent that we studied. But we can see here for the last 3 effluents, it could be with a high potential, it could be a good industrial application. For the conclusion of this presentation, we saw that depending on the organic composition of the effluents, we had two effects of the temperature, either low or high. We had different behaviors for the heating period and the oxidation duration, and this allows us to know the adaptability of the water oxidation depending on the industrial effluent. We were able to monitor the decrease of the organic fraction throughout fluorescence spectroscopy, and this data could be complementary to the COD and TOC, and also this particular application is not developed in literature. We show that we had a high potential of treatment for a majority of effluents, and all this data could be a decision support tool for industrial applications and to see whether or not it applies to the regulation. And we validated the treatment path for all effluent except the paper effluent. For the perspective of this study, we would like to perform some continuous experiments in the bubble column, which is the form that we find in industry, to validate the performances, but also the autothermicity of the process. Thank you for your attention.